Given the functional similarity between motion planners and controllers, you might wonder, why don't we use the same algorithms for developing both systems? The answer is yes, it is absolutely possible. In fact, the first motion planning algorithm that we will study and that we will implement in the upcoming laboratory lesson is borrowed from the control theory and is the PID algorithm. This algorithm will allow us to implement a path tracker that is a motion planner that ensures that the robot closely follows the path calculated by the planner. Interestingly, the path tracking algorithm that we will implement in this section of the course shares many similarities with the line-following robots. In those cases, instead of following a virtual path calculated by the planner, the robot must identify and must follow a physical line drawn on the floor, essentially a path traced in the real world. The only difference with the algorithm that we will implement here is that instead of following a visible line, we are going to use the path that is calculated by the planner as a reference, that is kind of an invisible path. This also means that once you understand and implement the path tracking algorithm in this course to follow a path calculated by a planner, you can reuse it to follow actually any line that you can draw on the floor. Does it sound challenging? Actually, some curious students have already modified their bumper bot to implement this functionality. So, how does this algorithm work? Let's consider a robot associated with a reference frame that needs to reach a certain destination by following a path that is calculated by the planner. Path tracking algorithms progressively calculate a point along this path in the direction of the goal that is at a fixed distance from the robot. If we consider a global reference frame on the plane where the robot is moving, then in this reference frame the robot will have certain coordinates that we can call xr and yr, and instead the point P on the path will have other coordinates that here we called xp and yp. Path tracking algorithms compute the error between the robot's current position and the desired position on the path and calculate a velocity command that minimizes this error. In this case, as we can see, since the point P lies directly in front of the robot, there are no error components to minimize along the x-axis, and so the path tracking algorithm will just move the robot forward. As we know, motion planning algorithms are executed repeatedly, and thus these path tracking steps are iterated until the final position is reached by the robot. So, following this velocity command that was calculated by the path tracker at the first interval and then that is sent to the robot, then the robot's wheel will spin and so the robot will move, changing its position on the path. Again, in this new position, the algorithm calculates a new point, so a new point P on the path that is in the direction of the goal and still that is set at a fixed distance from the robot. Once more, the coordinates of this point and the coordinates of the robot are calculated in the global reference frame, and once more, the error is calculated as the difference between the robot's position and orientation relative to the point P on the path. In this case, the error composition is a bit more complex. In fact, we can see that there is a component of the error along the x-axis, there is another one along the y-axis, and also we see that there is an orientation error, so the robot must turn. This means that the velocity command that the algorithm must calculate in this case is both one command that translates the robot and also rotates the robot, so it will have to move forward and turn left, and so on. In each iteration, the robot executes the velocity command that was calculated in the previous iteration, and so it is moved to a new position of the map. And then a new point P on the path is calculated in the direction of the goal. The new coordinates are calculated that are used just to calculate the error, so the error variable along the three components of the pose of the robot, so along the x-axis, the y-axis, and the orientation. And so these steps are repeated until the final destination is reached. At this point, the point P that is extracted from the path exactly corresponds to the destination and therefore also to the current pose of the robot, as the robot has already reached the desired destination. Thus, the coordinates of the point P are equal to the robot's coordinates, and so this means that there is no position error to correct. And since the position error and the orientation error are both 0, the path tracking algorithm doesn't need to minimize anything actually, and so the velocity command that it sends will be 0, and so this will just stop the robot as it already reached the final destination. But Antonio, how do we use this algorithm to track a black line that is drawn on the floor, and not just a path that is calculated by a planner? Well, the only difference between tracking a path that is calculated by a planner and tracking a black line that is drawn on the floor lies in how the point P is calculated. This point has to be on the path that we want to follow in the direction of the goal that is at a fixed distance from the robot. The only thing that changes is the method for determining the point P that we want to track, and so the point that we evaluate to calculate the error variable that we use in order to produce a velocity command. For a virtual path calculated by a planner, this point is determined by reversing the path and extracting the last point on this path whose distance is greater than the fixed distance that we set from the robot. For a real path instead, that is traced, that is drawn in the physical world, in the real world, the algorithm for calculating P, so the point P on the path, is a bit more complex, as it involves using vision systems to detect the line and then to extract a point from this line that is at a fixed distance from the robot.